So let me first thank the organizer for inviting me. So I wrote an abstract with a hope that I would put pressure on myself to produce material I would present here, but of course I didn't quite have the time to do that. So perhaps I will talk about something that is slightly different, and perhaps a better title would have been Saddles and Spikes, even though this might sound a bit uncomfortable physically. So this is within a research program which I might call relativistic cosmological modeling. And with this I mean that kinematically we have, I'm restricting myself to 4-dimensional spacetimes with a Lorentzian magnitude signature. We have matter fields in cosmology. With the advent of dark matter and dark energy, there are lots of matter models going around. You have to have something, but it should be compatible with large-scale structure and associates its simplification with this. We have dynamical laws, which I split into dynamical laws in curved space-time geometry and dynamical laws for the space-time geometry. These are sometimes intertwined, but it often makes sense to distinguish them because some of this is valid for any of these theories. You have to have, so this is what explains relativistic. What is cosmology then? Well, we have to have some boundary conditions. So what are cosmological boundary conditions? Well, sometimes you have symmetries like spatial luminate, and then it's pretty obvious. Otherwise, it's more difficult to actually spell out what you mean with cosmology. And I actually think that often when you talk about cosmology, you're actually talking about the interior of black holes. And in the end, you have to say something about how this is related to the world. How to make this more specific then? Well, a common lessons for anything in this area are the following. So there are model hierarchies, and this goes back to, say, Newton. You start with the simple and go to the more complex things, but here it actually takes on specific meaning. So in all these geometric theories, there are geometric symmetry hierarchies. And in particular, there are preferred symmetries. So Killing vectors and homothetic Killing vectors, there are also affine and curvature collineations. So they are compatible with what you are doing, which, for example, proper conformal motions are not. And that's why we have so few conformal proper motions in relativity and other theories. And you can use this. You also have discrete symmetries. So you can have hypersurface orthogonal Killing vectors, hypersurface forming ones, and so on. And this gives you a hierarchy of Lie contractions that you can contract from a more complicated model to a more simple one, from Bianchi type 9 to Bianchi type 7 to the Bianchi type 2 to Bianchi type 1, or from locally rotation symmetric Bianchi type 9 models to Cantor-Sachs models. And if you formulate the equations in a nice way, you can obtain all these structures as boundaries of the more complicated spacetimes. And you can even do this asymptotically in the generic case. And when you want to understand more difficult models, you have to understand these simpler models. There's no way around it. The same thing happens with sources. You have source hierarchies. For example, if I take since you are sitting here, the scalar field description of a Chaplygin gas. Asymptotically, it's described by exponentials, and you have to understand exponential potentials in order to understand the dynamics of the Chaplygin gas. So if you have a dynamical systems approach to dealing with that, you can obtain these exponential boundaries, so to say, of the full state space, which provide the building blocks for understanding the full case. And this is not a coincidence, because the exponential potentials are allowing you that you have self-similarity. So this corresponds to that this problem have asymptotic self-similarity, and the scales you are putting into it corresponds to asymptotic self-similarity breaking. And this works for basically any sources that you have these hierarchies, where you can, if you formulate the problem in a nice way, can get simpler pieces which you then can combinatorically build up the more complicated dynamics with. When you are facing this, you have to set yourself somewhere in this hierarchy where the more general case is contextualized. And you have to do an analysis of what you are doing. That's a key. That's a point of doing it. So you have to start with some state space analysis of the true degrees of freedom. People often skip this, and it leads to very bad consequences. You need a complete state space adapted coordinate cover. You need to respect the state space topology, including when you have space-time boundaries to which state space boundaries where you can actually extend the equations to cover them. Because typically, asymptotically, things comes from, say, if you take the Chaplygin gas example, from the exponential boundary. That's the asymptotic states of the problem. You need to do a local and global dynamical systems analysis. Fixed point analysis is not enough. And you have to make a physical solution space interpretation. I often see that people do just fixed point analysis, and it actually corresponds to that you have coordinate singularities in your coordinate cover of the state space, which means that this is completely physically irrelevant. So let me exemplify this with 3 different examples, where my first example is a very simple example. So FR gravity with R plus alpha R2, spatially flat Robinson-Walker cosmology. So this is at the bottom of FR gravity, basically, the simplest possible model. So this is work together with Arthur Arlo and Sante Carloni. So you have 3 essential equations for the Hubble variable, that's an expansion, Riemann curvature, and Riemann curvature scalar, and its time derivative. The scale factor due to the problem decouples. You have a second order, you have an R dot dot equation, and you have an H dot evolution equation. So effectively, since we want to use dynamical systems to get the first order problem, we use H, R, and R dot as our variables. Since it's a gauge theory, you have a constraint. And the first thing to analyze in this state space, described by these 3 variables, is the constraint surface. So how does a constraint surface look like? Well, it's a quadratic form. And in order to see how the state space actually look like, we bring it to canonical form. And this is just a linear transformation. You just don't want to do that. You want to do this in a dimensional sensible manner. So you look at the dimensions of the different quantities, and then you scale variables so that you get the same dimension of your different variables. And then you get a bunch of variables looking like this. So your state space is actually a light cone. That's how the state space of these models look like. You have a discrete symmetry connecting these 2 things, and you have a Minkowski fixed point here, which is completely non-hyperbolic because it's a conical singularity in the state space. Because of the discrete symmetry, if I know the solutions here, I know the solutions here, so I only need to investigate one of these, the upper part here, preferably because here the Hubble variable is non-negative, while it's where less or equal to 0 here, it's larger or equal to 0 there. So for a cosmological perspective, let's take this. But if we have this, we have everything. We cut out the fixed point here, the Minkowski state, because we want to analyze this part of the dynamics. So then we go on, and I basically now choose new coordinates. I'm going to project things so that I'm going to have coordinates which are circles here, and then I'm going to numerate the circles in a bounded way. So projection, I get this, the constraint looks like this. I introduce global coordinates for this constraint. I choose a new variable. This t is basically the t in the superspace of these variables, which goes between 0 and 1 by definition. Everything is dimensionless. I get a completely regular system. My state space is now a cylinder, a bounded cylinder going between 0 and 1. I can extend the equations, the state space to include the boundaries, because all asymptotics are going to be at the boundaries where t equals 1 corresponds to the Minkowski state space, Minkowski fixed point. This also corresponds to that I've blown up this non-hyperbolic fixed point, the Minkowski fixed points. This is the complete solution space for these models. I should also have said that the Einstein frame part of this is the gray area here. It's not an invariant subset. It never is. You always have solutions going from the Jordan state space and between the Einstein frame state space. We find monotonic functions, Liouville functions. We prove that this is how the solution space looks like. There's no room for discussion. This is a complete state space. There is one solution coming from here. This turns out to be 2 zero eigenvalues. But that's not so bad, because this is a nilpotent fixed point of first degree, which means that you know how to blow it up, which means that you can get a new fixed point, which this corresponds to center manifold. This is the so-called inflationary attractor solution. And it also always looks like this when you have inflation. You have one solution coming from a quasi-de Sitter state, where the deceleration parameter in the Jordan frame is -1. It's called inflationary because nearby solutions, because it is a saddle here, it's a saddle solution, are squeezed to it here. The real attractor is not this solution. It's this, which describes, it's a limit cycle of all solutions ending up here. And the reason why every nearby solution follow this is because of the saddle nature here and because you have a common attractor up here. It always looks like this in inflation. You have a center manifold here. That's what allows you to have sufficiently many E-folds. Then you can go to the Einstein frame. It's described by the gray area. You then get coordinate singularities because you are breaking down your state space variables when you do this transformation to the, to the Einstein frame. You get a fixed point corresponding to that solution. You get a fixed point which is a source corresponding to the coordinate singularities you have here. And this is a standard potential we saw in the previous talk also describing this. So which one is most fundamental? The Jordan state space or the Einstein frame state space? Solutions are conformally extended from the Einstein frame to the Jordan frame here. You don't see this if you just use the Einstein frame. Then you think that you have a source describing this part here. But from the Jordan state space, it's no problem. You can go ahead. Which measures are you going to use when you're done? Because you always get the measuring problem when you have this situation where you don't have a real attractor here. Are you going to use an equivalent space for the Jordan state space or for Einstein frame state or for some other measure and so on? And you get endless discussions. I'm not going to go into them. This is how the solution space looks like. You can do dynamical systems methods to actually produce approximate solutions for the whole evolution for all orbits from beginning to end to arbitrary accuracy. I can give you everything you want. And the question is, what does it mean? So this is the first saddle we are seeing. Let me now go on to another type of saddle, which appears in perturbations of lambda CDM cosmology. So this is also work with Arthur Arlo and John Wainwright. So we have done this for multiple fluids, scalar fields, for an increasingly complex set of problems where we can use dynamical systems methods to describe perturbations. John Wainwright and I have also solved the problem in terms of analytic functions and a quadrature up to second order for lambda CDM explicitly for the first time. Also for the super horizon limit. We have not published this yet, but by looking at it. But whatever model you have it by now to compare it with lambda CDM, because lambda CDM is its simplicity and its amazing observational compatibility, even though there are some problems. It sets the standard for what you are supposed to beat if you are going to do that. Also, you have an analytic solution for the problem, even up to second order, as I said. So this makes it a good test case with what you can compare whatever thing you want to do. Oops. So here, these are not the best variables to actually solve the problem, but this is how it's often presented. So you take the co-moving density perturbation, you have a second order equation, you have background matter described by omega m here, which you can describe in terms of a normalized scale factor parameter. I'm going to use e-fold time. I'm going to transform it using the linearity to a first order equation. I'm going to use effectively a background variable as an extra variable. So what you have typically is that you have a background set of equations. In this case, it's trivial, but I could have several scalar fields, fluids, then you have a bunch of background state space variables, and on top of that, like a fiber, you put the perturbation equations, and you have a bunch of perturbation equations, but you can play the same game. This is effectively using this as one variable and this as one variable. I introduce polar coordinates. So this is r times cos theta. This is r times sine theta. Thanks to linearity, the scale variable drops out. So this is tangent theta. If this is sine and this is cos. Herefore, you get simpler equations if you do it like this. But this is actually 2-to-1 mapping of the full state space. So one should be aware of that. These equations you can solve, but you can also just train by doing dynamical systems method, looking at it, and do the full dynamical systems analysis. So this is a real state space, the cylinder here. And this is in YV, which is then have to be traversed twice in order to get the real picture. You can do that, but you can also explicitly solve the problem. You don't need to do a Fourier decomposition because the spatial derivatives drop out of this problem. So the constant of integration are actually spatial functions, C plus and C minus. And you have one integral here, which you can describe in terms of a hypergeometric function. You can do this to second order. This is the only non-trivial algebraic function you have in these problems. In this, if you now plot this, again, we have a saddle here. Setting C minus 6 to 0 gives a growing mode solution. The other generic solutions are going here, going backwards in time towards a singularity, because this corresponds to a quasi-isotropic singularity. Here, shear, Hubble-normalized shear is growing. This is what's happening here. I can now have these spatial functions so that at the point, or a line, or at the surface, so at one spatial variable, I'm just hitting those solutions are quasi-isotropic singularities. All others are not quasi-isotropic singularities. This is an example in this perturbational context of what we call a spike, a permanent spike. And you can, of course, use this symplectically and quantize it. So this is the simplest possible start to start quantizing spikes. I would say, take this model, for example. One can also compare the result with a full state space picture, all of general relativity. I'm contextualizing this in a full state space. Then this gives a fairly good approximation. We can compare if second order approximations give a better approximations when we compare the perturbations with the true Einstein field equations. This is pretty good. Here it becomes invalid. So this part of the perturbed state space is really physically irrelevant. The spike is the beginning of a spike here. This is where physics take place. And here you end up with a de Sitter state with a particular. This is also the de Sitter state, but at a different rate you're approaching it. And I'm doubtful that is physically correct when one looks at this. This is what people are interested in. You say that you take the growing mode because it's a saddle, so nearby solutions are squeezed to it. And then you end up at a local attractor, and that's why you are also continue to be squeezed at it. So that becomes a better and better approximation for this nearby solution. But again, what measure should you have? Because if I'm far away from it, I never come close to this solution. So why should you rule out those solutions? In this case, it happens to be unphysical, the perturbations. But still, it's the same problem you face in general relativity or any of these theories for that matter. So, as I said, we can compare this with what's happening in the full state space of general relativity, which I'm now limiting myself to here. In the first paper, where we started to address this general problem, was in 2003 with George Ellis and Henk van Els. It's called the past Attractor in Cosmology, where I introduced this asymptotic silence business. But it's interesting also to see how asymptotic silence can be broken. We were forced to distinguish different concepts. Asymptotic silence turns out to be necessary but not sufficient for BKL. This, in the next talk, we're going to hear about oscillating spikes. They are also asymptotic silent, but you don't get this described by ordinary differential equations. You get it described by inhomogeneous solutions. Because in that case, inhomogeneities are trapped by shrinking particle horizons instead of spread out from them. So here we look at Weyl scalars. I took a couple of special solutions just to illustrate this. I will also take a picture from Weichet's thesis. So this is a Secker solution, a very simple solution. You have an x-dependent, here it's plane symmetric. Take the simplest possible to illustrate the point. So this is my final slide. So you have initial data at different spatial points. You evolve them in this Hubble or expansion normalized state space of relativity, where you get the spatial luminous models on the boundary of the full state space at each spatial point. So the issue is, do you approach it or not? If you approach it, that corresponds to BKL. If you don't approach it, that corresponds to BKL violation. So you can view that in a full state space. And you can situate these perturbations, that's what I had intended to do here, in that state space to assess to what extent standard perturbation theory gives correct results to tangential field equations, to assess if second-order perturbations give better results than first-order perturbations, and to what extent, if they do that, they do improve the situation. Anyway, here is a profile. Just like in the previous case, we have an isotropic singularity here. So the data that happens to be such that you have a zero in this shear mode here, they go here. But if you don't have that, these points will go to this point, and this on this side will go to that point. This point corresponds to the local rotational symmetric Bianchi-type 1 solution, which is the singularity in Schwarzschild, which you see in the conformal diagrams on the top. This is exactly that asymptotic behavior. This is a called tau point, which corresponds to that you have the tau representation of Minkowski spacetime. Now you are perturbing that, so you are not going to go to the, but that typically corresponds to horizons. It also corresponds to weak null singularities. It depends on your model here, what's going to happen here. But here, if you have, say, a point going to this, you have one point which goes to this isotropic singularity. You have one that the other solution is going here. This part corresponds to an asymptotic silent part of the, you have particle horizons on computed geodesics here, become smaller and smaller and smaller. So this is what happens in Schwarzschild, for example. But you have, here's a geodesic from this part. This happens to be a well, time-like singularity going here. And here asymptotic silence is broken in that case. Typically, but not in this particular example, where this is from this paper, asymptotic silence breaking. By the way, the first page here, you have the shape parameters locally described and also the history behind it. So it's not just Kastner parameter. This corresponds to self-similar states. So this is described here. You might want to look at that. And so here you often get weak null singularities. You typically, when you look at explicit solution with this spike perspective, find out that you typically have a space-like singularity with asymptotic silence and a weak null singularity attached to it, even though there's a different singularity in this case. And there are also other indicators that weak null singularity are closely connected with BKL behavior. So saying one or the other, that's I think that's a very bad idea. And why would you have this connection with weak null singularities if we were actually talking about cosmology? I think it's much more likely that we're talking about the interior of black holes. A permanent spike like this, so you actually get to specific limits for each and every one, except here you have a certain thing that blows up. This means that you have asymptotic self-similarity point-wise. Generically, this is not going to happen, and this is going to be the next talk by Werchet here. Permanent spikes are non-generic. But still, you can start to investigate them as a first step, because the next step is going to be much, much, much more difficult. When you have a one-parameter set of saddles, like you have in Kastner, hyperbolic set of saddles, transversal hyperbolic saddles here, you will have spike oscillations taking you from one state to another, also described by the BKL map, but skipped twice, as we are going to see next. This is much more difficult, so I will leave that to the next speaker. Thank you.
I'm not quite understanding why you say you cannot distinguish between weak null singularities and BKL singularities.
Yes, you can distinguish between them. If I said that, that's very bad wording. They are very different. But there is a connection between them. That if you look in a full state space, examples where you have weak null singularities appear quite close in the state space to what, if you take BKL dynamics and look at the BKL Kastner map, the probability is one that you're arbitrarily close to this tau point. And the tau point is associated with another invariant subset in the full state space where you also find weak null singularities. So I think it's not unreasonable to think that you could have a space-like singularity attached, like in this other example, with the weak null singularity. If that's the case or not will depend on the initial data. My guess is that it depends on the strength of the initial data, how big a piece of a weak null singularity you attach to a space-like singularity. But it is striking that you sort of in the full state space of relativity, when you have normalized it, find that they are so close in that state space. I don't know if that has a deeper meaning. But it makes me think that maybe one shouldn't be so hostile, which people before have been between, oh yes, weak null singularities, BKL is irrelevant. No, it's BKL. I think that's a stupid attitude when one looks at the state space. That's the very modest thing.
I push back against stupid, but I understand what you say.
Very good.
Okay.
Okay.
All right, so let's thank the speaker again.